right, so I'm James Qualls, principal engineer at a startup called Discern. We're kind of focused on helping people manage their legal entities and tracking their state standing with Secretary of State, filing new registrations, automatically filing annual reports and franchise tax, and acting as a registered agent for those people. Today, though, I'm going to talk to you about how we improve developer velocity by deploying scalable preview environments using GKE Autopilot and Dagger on every pull request. And for those of you who'd be looking for some code, I've got this QR code and this link. The code's not live yet, but you can expect that the repository will be filled out with some sample code that we'll go over later. So shared environments. We've all experienced the hassle of shared environments like staging and user acceptance testing. And over time, these environments can become a maintenance burden. So as your team grows, they usually end up competing with one another. Sometimes the contention grows on a main branch and you're deploying to a single environment. Root cause analysis in that single environment becomes difficult where there are many changes being merged simultaneously. So if you have 10 PRs that you merge and something goes wrong, it might be difficult to discern what caused the issue in the first place with many pull requests being merged. And then, of course, over time, stale data makes automated end-to-end tests unpredictable, and unpredictable tests are just really annoying. So solution, preview environments. But what are preview environments? So preview environments are temporary copies of your application deployed every time a developer pushes code, and they should be accessible via a unique URL, something like pr100 preview.domain.com. And then they should be easily cleaned up and destroyed. This is a really important one. So we don't want our infrastructure kind of sitting around and getting stale and wasting resources. So they should be deployed on demand and destroyed when they're no longer needed. And then by utilizing preview environments, developers and QA testers and project managers can test and validate changes in a production-like environment without affecting the main branch or existing production environments. Now, some of you might be using other platforms like Heroku and Vercel, and you might be like, I already have this thing, so why are we talking about this? These platforms do support concepts of preview environments, but they often lack backbone dependencies like databases or queues. Can be done, but it requires a little bit more orchestration. It can be difficult. You also, on these platforms, don't have control of your infrastructure, and they don't usually fit the needs of larger enterprise applications with more complex topologies. So in this talk, we're going to be focusing on how we do this with Kubernetes. So what does this pipeline actually look like? For us, it's as simple as make CI/CD deploy. High-level overview of how this works. We essentially have a simple go run command that's underneath that make command. Dagger will effectively build all of our container images. We have a Remix React front end. We have a Golang API server on the back end. Postgres, we're just shipping the standard image for Postgres, and then we're building our own custom temporal light image to keep that up to date. We found that the branch on main for temporal is not always up to date, so we have to pull that and update the image for ourselves. And then we also do some custom things with that as well. At the end of that whole system with Dagger, we are pushing all of those images to the container registry, and because we're inside of the Dagger Go SDK and we're able to run this. We can kind of like add additional layers to our deployment pipeline. So once we have all of our artifacts in the registry, we then generate a Kubernetes manifest, which acts as a single deployment. We apply that to GKE Autopilot, and then we wait for the deployment's pod to enter its ready state. And then we apply migrations by querying for that pod's IP. And I'll go over how we do that in a later demonstration with some code. So what does the infrastructure look like that this is actually deployed to? Because the GKE Autopilot thing is fairly ambiguous, but this is how we have ours set up. So at the very top level, we have Cloudflare, which we use for WAF and DNS and wildcard certificates. The wildcards are pointed at a Google global Anycast IP. That IP address is attached to a single global HTTPS load balancer, and that load balancer is configured via Kubernetes gateway objects. Those gateway objects are custom resource definitions inside of the GKE Autopilot cluster. And if you're using 1.26 or newer in Google Kubernetes engine, these should be enabled by default. So the way that these will essentially route is we have our deployment separated by a namespace. If you're in the preview namespace, we deploy all the preview versions of the application into a single namespace. This makes it really easy for us to clean these things up, keep them isolated from the production resources. And then on the production namespace, we essentially just change the domain that we're deploying, and then also some configurations. So we're pointed at different resources. And then we'll kind of talk about what the shape of that deployment actually looks like. So in each one of the deployments, they have a label that's associated with the pull request so that we can easily query the Kubernetes server and find all of the pull request related resources and destroy them. Each component is defined as a container inside of the pod. This simplifies a lot of things for us because we don't actually have to configure the application to behave any differently than it does when you're running it on your local machine. Typically, if you're running all of these components locally, you're going to start, your front end server, you'll have it pointing to your API, and then your API will be pointed at both temporal and Postgres. But they just get to communicate on localhost 127.0.0.1. And then we attach a persistent volume claim to Postgres so that we can have persistence in this environment. If GKE Autopilot reschedules any of these workloads, we don't actually lose progress in that environment. But once everything's destroyed, the persistent volume claim goes with it, so the data is no longer sitting around. And that's destroyed at the end of any pull request. Once a pull request is merged, all of the resources that are in that namespace with a particular label, a GitHub label that contains that PR's number, those resources are all destroyed. So now let's get to the fun part. Now I'll show you some code. So I will flip out of here and we'll take a look at how we have things set up with Dagger. All right. So we'll clean this up. Can everyone see my code window?
Yes.
Looks good. All right. So high level, we have our main entry point. We load some simple configuration from the environment, and this happens inside of GitHub Actions. We'll load a few environment variables that become available to us, and then we set some defaults here. So we grab the GitHub repo, the current reference, the actor, the pull request number, which once you've merged this into the main branch, if you re-execute the same GitHub action, this variable might not actually be available. So you'll have to set it to some default value. And then we have something that controls the base deployment URL, and then we manipulate that depending on whether there's a pull request number available. The Kubernetes namespace that we want to deploy to, which by default is preview, and we can control that based on if we're on a pull request or whether it's been merged into the main branch or whether it goes to a release branch to deploy to production. So if we bounce back out of this load function, we can kind of see at a high level what we're doing. It's very similar to the diagram that I demoed before. One key difference is the diagram was kind of set up so that it looked like we're kind of building all of these artifacts in parallel. And while technically we could do that, we don't necessarily need the speed gain at the moment. So this is all happening in serial. So essentially we'll search for the repository root. We will then parse our deployment URLs and our artifact registry URL. We'll instantiate an instance of a Kubernetes client. And this is using the native Go SDK. For Kubernetes under the hood. And when we initialize this, it basically just loads whatever environment config you have. So if you're running this in CI and you've used a Google Cloud command to configure the current cluster by calling gcloud container clusters get credentials, that will automatically configure the kube config file in that location. So this kube client should be configured based on what the current kube config file is set up to do. We'll generate new URLs from our base registry URL. So we have our backend server and then our dev temporal image. We will then ask Dagger to build us an image, and we'll get back the image ref. This will both build the image as well as push it to the container registry. So we'll get back the full hashed image reference. We'll then build our Go image. Same thing. We get back the hashed image reference. We have some dependencies between our front end and our back ends. We produce an open API spec based off of our API server. So we take that generated open API spec, feed it into the front end image, and we use that to generate some client code that helps us bind the API contract with our front end. And then here is where we get into the Kubernetes orchestration. So we'll take all of those Docker image references that were produced by Dagger. And then we're also using another library called CDK8s. Makes it really easy to generate manifests for Kubernetes applications. It has a couple of really nice features. For example, every one of the applications when they're deployed will get a unique hash, which is useful for the naming conventions on the deployment and the pod. Specifically, the tags will make it easy to separate them so you don't have traffic routing to the wrong pod. But these labels can be a little bit tricky to manage, and CDK does this nicely. It also lets us import custom resource definitions so that, for example, with GKE 1.26, the gateway API, the API that has resources in it that you would need to route traffic correctly based on headers or based on a specific path, that beta version of the API, it's nice to be able to import that and keep that up to date. So CDK8s will let you import that into your Go SDK. So if we quickly just kind of look through this configuration, if we jump to the container definition function and we expand some of this, we can kind of get a look at how these are actually building up. But we deploy all of these components simultaneously. So we deploy a front-end image, the back-end image reference, the temporal light image container, and Postgres. One really important thing to note here is with your liveness and readiness probes, to make sure that we wait for the application to become healthy, we make sure that we set these readiness probes and they test individual things for each application. So our front-end and back-ends have their own health check endpoints. Postgres is actually running a command probe. PG is ready. This is a binary that's available, or a script that's available inside of the Postgres container. So you can wait for the Postgres instance to be up and serving and ready to serve traffic. It's better than just a blind TCP check. So now if we go back to where this function is being used, we feed in all of these references. We produce a set of services, and the services are necessary to bind to the HTTP routes. And the HTTP routes are the custom resource definition for the Kubernetes gateway objects that I was referring to before. And these gateway objects are bound to, and the controller inside of GKE Autopilot will reconcile these HTTP routes and dynamically route traffic based off of what those routes are pointing to. So if we expand the routes, we can kind of see how we do this here. We have first the host name, and the host name is derived from what I mentioned above. We calculate the preview environment name based off of the pull request number, and then we build a set of rules which tell this HTTP route how this host name should route traffic. So by default, everything goes to the front end. We have an additional API route. You can ignore this commented out stuff, but we have an additional route that goes from the front end, and we also expose the temporal UI so that we have easy access and we're able to debug those things quickly in our preview environments. Cool. So now once we've generated this manifest, this basically produces a really large, disgusting YAML object, but because we get to manage this in Go, we get really nice type safety and guarantees around being able to build that manifest. And we also know what options are available to us at any time, depending on what version of those APIs we're using. Then we call apply. This is basically just doing a kubectl apply under the hood. We produce the manifest, apply it to the cluster, and then we use a wrapper around kubectl rollout to wait for the status of that deployment to reach complete. And then once that's done, we know that Postgres is ready. So then we will query for the pod that belongs to the deployment for the application that we've just deployed, the Postgres container inside of that pod, because they're all running together in the same instance. We basically can just get this pod's IP, even though all of our applications are running inside of a single pod. Postgres is exposed on its standard port. So we could basically just generate a database URL with the pod's IP address. And there may be some questions around, if we're querying for the pod's IP address, how would this work if you're running this locally, or how would this work if you're running it inside of something like GitHub Actions? We actually use Tailscale for exposing access to our Kubernetes cluster to both GitHub Actions and as well as to engineers on our team. So this gives us sort of a magic layer where no matter what network we're deploying on, we kind of magically have access to the same 10 dot space that our private GKE cluster is running on. Once we've gathered the database URL and we've waited for the application to reach its ready state, We're also using another Go library, Golang migrate. We use this for both running migrations locally when we're developing, but we can also just sort of embed the migrations in a Go binary using Go's standard Go embed. And then we build a migration object, and we just call migrations.up against that database URL. And voila, we now have a preview environment that's exposed per pull request. And then we have an additional destroy workflow that will take this these same selectors and locate all resources when the pull request is merged and destroy all of those existing resources inside the preview namespace. And that's it.